Okay, very good. So remember we had this Mg closed Riemannian manifold. So we discussed two counting functions. Generating function for eigenvalues. One was this ZMT, which is some exponential of minus lambda I t. And then I said that there is an asymptotic expansion of this form 4 pi t, the power minus n over 2 times a0 plus a1t, a2, t2. So this was, this is partition function, this is the heat trace expansion. Of course, n is dimension of the manifold. And then we started talking about a second type of generating function, which also kind of packs information into analytic gadget of this form, zeta ms is a sum 1 over lambda I to the power s. But this time we can only sum over non-zero eigenvalues, obviously. So we saw that Boyle's law implies that this function is holomorphic on real part of S bigger than n over 2, which is dimension of m over 2. And it's certainly, as we observe, it's certainly singular at s equal to dimension of m over 2. And singularity, at least from right-hand side, at s equal to dimension of m over 2. Okay. So as I said, our first goal now is to show that this function has a meromorphic extension to the whole complex plane and find location of its poles and get some information about its residues at those poles. Nature of poles, for example, are those poles simple or non-simple, and what are the residues at those poles? So, okay, so this is spectral zeta function. This is some sort of theta function. And now the idea is to link these two things together, and the link is via Mellin transform, which involves gamma function. So the formula that I want to write one kind of slogan. If you remember this slogan, this will help you a lot in mathematics and physics. So basically, the slogan is that Mellin of theta is equal to zeta. It rhymes, right? And you can also ask kids to memorize this. Mellin of theta is equal to zeta. Basically, the idea is that Mellin transform of this first gadget is the second gadget. So let me explain this, and then we'll use this idea. It's a major idea in number theory, spectral geometry, and physics to relate the two. Without this, it's very hard to prove anything I'm going to prove today. So one gadget that we need is gamma function. So gamma function, I defined gamma of S, you remember, as integral 0 to infinity, e to the minus t, t to the s over t dt. And I said that it's very easy to see that this function is holomorphic for real part of S positive. So this is elementary to see. Holomorphic in real part of S positive. So at least on this right half plane, this is a nice holomorphic function defined for all values and it's positive. Okay. You can also easily check to see that just simple manipulation of integral, easy to see that gamma of S plus 1 is equal to S gamma of S. Okay. So this is again for real part of S positive, so that both sides are defined, so we can just go on and prove it using elementary things in the integral. So, I mean, one of the things from here, of course, follows that gamma of n is equal to n minus 1 factorial. So the idea then is that gamma of S is kind of some analytic continuation of S minus 1 factorial beyond the integer values. That's the S minus 1 factorial. Of course, S minus 1 factorial function only defined for integers, but this function extends it as a holomorphic function to the whole right half plane. And if you're curious about gamma, there are some other conditions beyond being holomorphic in the right half plane and extension of this factorial function that uniquely characterizes gamma function with those properties. Certainly, extension of factorial function is not enough. Holomorphic extension of factorial function is not enough. You need more conditions. Once you have those in place, then there is a unique extension. Okay, so that's good. But now, what we want to do, we want to extend it to the whole complex plane. And this is called, by the way, functional equation. For gamma. So we can use functional equation for gamma to extend gamma function to the whole, as a meromorphic function to the whole complex plane, like this. So, I mean, you can just say, okay, from here you can just say gamma S is equal to gamma S plus 1 over S. Okay, so if you take this identity, you notice that this defines gamma S for real part of S bigger than minus 1. For real part of S bigger than minus 1. So all of a sudden, then you can extend your function in a holomorphic way. So everything here and here. So there is a pole here. This pole, you can see from here that S equal to 0 is a simple pole because gamma at 1 is regular, so it's like a regular function, non-zero regular function divided by S near 0. So this is a simple pole. And once you do this extension, you get a simple pole here, and then residue of gamma S at S equal to 0 is just 1, right? So we get residue equal to 1. So that's good. But then you can continue this game, and then you have, of course, so gamma of S equal to gamma S plus 2 divided over s plus 2 divided by s times s plus 1. This enables you to holomorphically extend to here. And again, you notice that s equal to minus 1 is a simple pole. And you can compute residue by looking at s minus 1 by looking at this expression. So this is almost like, well, this is like 1 over s times s plus 1. And you can find this residue at that point. And you can just, extend step by step. And you go on. So the final thing is that, gamma function has an analytic continuation or meromorphic extension to the whole complex plane minus points 0, minus 1, minus 2, minus 3. So this is very important. So the upshot of this thing is that gamma s has a meromorphic extension. Can you okay, meromorphic extension to C with simple poles at so now the poles are at s equal to 0, minus 1, minus 2, minus 3, so on, right? So we get all these simple poles. And the residue at these poles also, as I said, is very easy to compute. And the residue comes out to be then.
Sorry, if you move the camera a little bit to the left would be great.
So you mean like this, right?
Yeah, yes.
Good? Okay.
Yeah, yeah, very good.
Very good. Okay, so now we can just also say that residue of gamma s at s equal to minus 1 is equal to the simple computation minus 1 to the n over n factorial. And the function is holomorphic everywhere else. Just superpose at those points holomorphic. So in particular, then the function 1 over gamma is an entire function. So one of the things is that 1 over gamma, you should not worry about this function at all. This is an entire function. Entire, you remember from complex analysis, means that it's holomorphic on C. That's it. Entire function. So it has also simple zeros at these points with simple zeros. At s equal to 0, minus 1, minus 2. And it's nowhere else 0 because it's 1 over something. I mean, unless there is a pole, otherwise this function is not going to be 0, right? So that's what it is, 0 minus 1. Okay, so this information about gamma is extremely crucial for what we are going to do now, because just keep this in mind and remember how easily we found this. You just needed some idea about gamma, and then that's it. By the way, the values of gamma I wrote. Okay, so I just said gamma n, we know what it is, n minus 1 factorial. So that's for n bigger than or equal to 1. So there is one more value that we know, that's gamma of half, which is root pi. So you can say minus 1/2 factorial, just for fun, is equal to root pi. Because gamma of s is s minus 1 factorial, right? So this is 1/2 minus 1 is minus 1/2 factorial is root pi. I mean, proof of this is very easy, right? Because we just have to use Gaussian integration. I mean, Gaussian integral. So let's compute. We remember gamma of s was integral 0 to infinity e to the minus t to the s over t dt. So gamma s, so gamma of half 0 to infinity e to the minus t. So this is root t, 1 over root t dt. So if you use this formula now, the famous Gauss formula, I mean Gaussian integral formula, minus pi x2 dx equal to 1, right? This is the value of the Gaussian integral. This implies that this is equal to root pi. So that gives you root pi. So it's kind of funny that these are basically, of course, I mean, you can just shift it and then get new values, but these are trivial operations. Basically, these are the only values of gamma that we know. I mean, explicitly, I don't think we know many more values. Anyhow, this was just for fun that gamma minus 1/2 factorial is equal to root pi. But now let's go back to our original problem. So now the game.
I have a question.
Yes, yes.
Can I clarify something? The residue is at, you wrote s equals -1. Should it be s equal minus n?
Sorry? What was
the residue, you wrote down the residue on the left, on the left side of the board. Is it s is minus n? Yeah.
Yeah. Thanks. It's minus n. Yeah, of course. Minus 1 is a bit minus n. Yeah. Thank you. Yeah, that was yeah, this is the one. Right. Any other questions?
And could you repeat why it implies that 1 over gamma is an entire function?
Oh, this 1 over gamma. Well, I mean. We have to know that gamma is not 0 at other, I mean, doesn't have any other poles, right? The function doesn't have any other poles. Oh,
and does it vanish anywhere?
Gamma, no, it doesn't. I mean, it's more or less clear from the formula on the right-hand side. You can get it. And then by this sort of functional equation, you know that it doesn't happen on the left-hand side.
Okay.
Right? So, yeah, so this is, yeah. Any other questions? Or? Right. So, yeah, so these are now out of the way. So now let's go and relate zeta to theta and Mellin transform. So now this formula immediately tells us that lambda to the power minus s is equal to 1 over gamma of s integral 0 to infinity e to the minus t to the s over t dt. I mean, to get from this to here, this is more or less definition of gamma. So just multiply gamma and then lambda. And then you just change variable from t to lambda t, and then you get, oh, this is lambda t, sorry. And then you change variable from t to lambda t, and then you get this equation. So this is the key for us, if you want. This is essentially gives us Mellin transform operation. I mean, I don't want to define general Mellin transform because we don't need it. I mean, that just doesn't help us even to give a very general definition. But just think of Mellin transform as just this one. this kind of operation. So what you can see now what I'm going to do. I'm going to write this lambda I to the power s using this. And on the right-hand side, somehow partition function will emerge under the integral sign, right? So let's do it.
So, sorry, did you explain why this formula is correct, or are you going to prove it later?
Well, this formula, I said, I explained it, it is correct because I just gave the proof. Cross multiply gamma and then by lambda to the s, put lambda to the s inside. It becomes lambda t to the power s and then change.
Change of variables.
Yes, change variable from t to lambda t. In the original, you get this one.
Okay.
Because integrate lambda, okay, so I'm assuming, of course, lambda is positive, right? And this is for real part of s positive. And this is true in that range. I mean, that's, as I said, it's pretty elementary. But it's amazing how useful this identity is going to be. This is going to be making like magical for us now. Okay, so then we get anyhow. So we get that ZMT. So sum. Sum 1 over lambda I. Yes, to the power s. Lambda I different from 0 is going to be equal to 1 over gamma s. Okay, so then integral from 0 to infinity. And then I've got exponential of sum, exponential of minus lambda I t, t to the s over t dt. And now here is lambda I is different from 0. Just this. Okay, so this you can just write as 1 over gamma s, integral from 0 to infinity. Okay, now we have to make some simple assumption. Okay, because all eigenvalues are here except 0 eigenvalue, right? So the 0 eigenvalue is missing here, although it's in Z, it's here. So how many times 0 appears as lambda 0? Well, the multiplicity of 0 eigenmode, right? So for connected manifolds, I can assume that, I mean it follows, as I said, that multiplicity of 0 is 1, because that's the number of dimension of a space of harmonic functions on this compact manifold, which is 1, right? So then I can just, in other words, write it as ZMT minus 1. So this is very important. You have to subtract. If you don't subtract, even the integral is not defined, of course. Then this is t to the s over t dt. Okay, so that's and that's zeta function, spectral zeta function. So we have this formula so far. Okay, so now what we are going to do, of course, now I'm going to use this. Oh, this is wrong because the other parts is erased, so I should not put it here. Okay, so now I'm going to use this asymptotic expansion for this, and then I will get information about this integral. And okay, first of all, the first step is to write it as sums of two integrals. So this is equal to 1 over gamma s. So there is integral from 0 to 1, Zm t minus 1, t to the power s over t dt plus integral from 1 to infinity, Zm t minus 1 times t to the power s over t dt. Okay? So this is Zm now, I'm able to write it as is plus 2s. I mean, sums of two functions. Of course, this calculation so far is valid only for real part of S bigger than n over 2, right? So far, both of these functions, I mean, all these functions are defined for real part of S bigger than n over 2. I mean, dimension of m over 2. Okay, but now look at this first. If you look at this function, I mean, this is like 1 over gamma s integral 1 to infinity. I mean, not just this, multiplied by 1 over gamma s, which is this. This function actually has analytic continuation to the whole complex plane without any poles. So, where 2s, which is 1 over gamma s, integral from 1 to infinity, is at m t minus 1, t to the s, over t dt. Now, I claim that this has as an extension to an entire function to the whole complex plane. 2s analytically extends to C. Why is that so? The reason is that, well, this integral, the reason is that actually the right-hand side is even defined per se as an analytic function. You don't have to do any kind of magic, any gimmicks to extend it by some identity, a strange identity like gamma function or this sort of thing. Right? It's already defined by itself. I mean, the right-hand side is holomorphic for all S belonging to C. So the only thing that, now we have to see why that's the case, and that's very easy to see. The reason is that the integration is from 1 to infinity, right? This sort of ultraviolet so-called, it's ultraviolet. Divergences, we killed it. We just start from 1 to infinity, right? The singularity at 0, we killed it. It starts from 1, so there's no problem of this at 1. It's convergent for any S in C. Now, at infinity, if you look at Zmt minus 1, what is Zmt minus 1? This starts from the first eigenvalue, lambda 1t, and then there is the second eigenvalue. So if you look at it, you notice that this has exponential decay at infinity, right? So has exponential decay at t equal to infinite. Okay, so it means that, but this guy, t to the s over t, if you look at it, this guy is at most a polynomial function. I mean, s is some fixed complex number, right? It doesn't matter. It cannot overcome exponential decay. So exponential decay makes the integral completely convergent uniformly and at infinity. So this is a very nice integral. There's no problem. It's holomorphic. So we can just discard it from our construction and just focus on IS. Okay, for the first one. So
sorry, why is it okay to discard holomorphic functions?
Oh, I'm not saying we are discarded in that sense. I mean, so let's see what we are trying to do now. We are trying to show that zeta has analytic continuation to the whole complex plane, right?
Oh, okay, I see. Yeah.
So we just wrote it as sums of, on its original domain, we wrote it as sums of two functions. One of them has analytic continuation without any poles at all. And so we just discard it from our considerations.
Okay.
Now we're looking at the first part. And that's where all the trouble is in the first part. And that's where we are going to meet poles and residues and all these things, okay? So we have to deal with the first part now, which is so far only defined for real part of S bigger than n over 2. Any other questions? Okay, so let's look at now the first part. That's where we are going to use asymptotic expansion for the first part. So for I of S, remember it was 1 over gamma S, a holomorphic function, integral 0 to infinity. So this is that mt minus 1 t to the s over t dt. Now, I'm going to give you the essence of the idea. At the end of the day, you have to do a little bit of epsilon delta argument, but that's clear what you have to do. So imagine you can just formally replace Zm by its asymptotic value near 0. So I'm just going to write it like this. 0 to 1, sorry. 0 to 1. Zm, we know it's 4 pi t. It's approximated by 4 pi t minus n over 2 times a0 plus a1t plus a2 t2, so on. And then I've got to subtract 1, minus 1, and then we have t to the s over t dt. Okay, first of all, let's take care of this minus t to the s over. So this, you can write it as two things. 1 over gamma s, integral 0 to 1, 4 pi t, minus n over 2 times a0 plus a1t, t to the s over t dt minus 1 over gamma s, integral 0 to 1, t to the s over t dt. Let's look at this function first, second part first. Well, I mean, what is this function? 0 to 1. Of course, we are, for the moment, in real part of s bigger than n over 2. That's the original domain, right? So 0 to 1, t to the s over t dt. What is this function? This function is 1 over s, I mean t to the s, right? From 0 to 1. I mean, if you integrate t to the s, you're going to get s, t to the s minus 1. This is t to the s minus 1. So what is that? That's equal to 1 over s, 1, 1. So this is 1 over s. Okay, so the function, if you compute it on the right-hand side, far away, you're going to have 1 over s. So this function has analytic continuation to the whole complex plane, except at s equal to 0. However, there is 1 over gamma s. So it follows that 1 over gamma s, integral from 0 to 1, t to the s over t dt is equal to 1 over s gamma s. So this function, 1 over gamma s, has a first order 0 at s equal to 0 that kills that s. So this function is actually holomorphic everywhere, right? This is holomorphic. So I'm not going to discuss it right now. So this is just, I throw away again. So the core of the argument now is to look at this. Notice that we are using this information about gamma all the time. We are using things about gamma. I mean, I emphasize here this is holomorphic because I don't need it now, but I'm going to need it later on, this holomorphicity. so that I just focus to compute residues. I just focus on this part. I mean, these are. Okay, so now let's focus on this part. So that part is 1 over gamma s, integral 0 to 1. Okay, so let's write it like this. Sum. Yes. Okay. No. So I'm going to write it like this. Integral 0 to 1. 4 pi t. Okay. So let me not write again. I just use it from here. That's better. Now, this is an asymptotic expansion. I'm going to look at term by term of this asymptotic expansion and see what is the nature of each integral, if I can analytically continue separately to start with or not. So let's take a look at one of them. For example, the first one, 1 over gamma s, integral 0 to 1, 4 pi t minus n over 2, a0 t to the s over t dt. Again, you notice that this integral you can compute in a similar way. This integral individually is very elementary that you can compute. And well, what you get? You get 1 over gamma of s, 1 over 4 pi t, or 4 pi, sorry, to the power minus n over 2, integral 0 to 1, t to the power minus n over 2, plus s divided by t dt, right? Minus n over 2. I just 4 pi t minus n over 2. This is n over 2 here, yes. So this is okay. So now I can just write it as 1 over gamma s. 1 over, and of course there is an a0 here also. So this is a0, 4 pi, n over 2. So if you look at this, what is this function? This function is, antiderivative is t to the power minus n over 2 plus s times 1 over s minus n over 2, right? There is this factor 1 over s minus n over 2, and then this is s minus, this is the thing, right? Okay, so of course this is from 0 to 1. I mean, for real part of s bigger than n over 2, this is 1, so this is equal to 1 over gamma s, a0, 4 pi, n over 2, 1 over s minus 2. Aha. And we know that s equal to n over 2 is a singularity of the zeta function, spectral zeta function, from even without doing any of these calculations, right? And here we are getting a term which is of this form. Now I will show that if you look at other terms, you are not going to get a singularity like this at n over 2. Your singularities are going to be pushed back to n over 2 minus 1, n over 2 minus 2, and so on, and then we'll see what happens. Okay, so from this sort of calculation, immediately you notice the following thing. So let me erase here. So let me notice that. Of course, remember, as I said, a0 was volume of the manifold, right? And now if you look at residue of this zeta function, and s at s equal to n over 2, the only term that contributes to residue is this term. The terms after this, before this, and the terms from here, and the terms from that second part that I discarded, they are not going to contribute to residue because they are holomorphic. So if you just take the residue at n equal 2, n over 2, you get 1 over gamma of n over 2, whatever this number is, we know. So this is a volume of m divided by 4 pi to the n over 2. Because residue exactly sees this pole, takes it 1, and then that's it. So the residue of the spectral zeta function at top pole gives the volume of the manifold. Residue of the spectral zeta function up to some constant. Is the volume. I mean, volume up to some scale. So now, but we can continue same argument and then see that possibly another singularity could emerge from this term, from that term, from that term. And then we know exactly where those singularities are going to be. So let me just write it down. I erased the most important part I needed. So can continue. So I mean, we have this term, right? 4 pi t to the power minus n over 2. It was like ak t to the k. So we needed 1 over gamma s, 0 to 1. Then t to the s over t dt, right? So this integral again is elementary. I can term by term compute like here. So this is equal to 1 over gamma s, 1 over 4 pi t, 4 pi n over 2. And then I've got ak constant. And then, well, this integral we can compute. So we have to do it like this is t to the power minus n over 2 plus k plus s from 0 to 1. And this is equal to ak over gamma s 4 pi power n over 2. And then I've got, like before, but this term now 1 over s minus okay, so here we've got yes, s minus n over 2 plus k. Yes. So we see that this possibly a pole at n over 2 minus k could emerge, right? So now I'm not saying this is necessarily a pole because this is an asymptotic expansion, but away from this sort of things that we are doing, there's not going to be any other pole, and analytic continuation away of this point is guaranteed. So a possible second pole at s equal to n over 2 minus k, obviously, right? Minus 1. Third pole s equal to n over 2 minus 2, and so on. Okay, so now a picture emerged. That's so the upshot of this calculation. I did it in a formal way, but that's very easy to fix this sort of formality into, by asymptotic expansions. I mean, that's trivial essentially. So basically, what we can do is that we can prove then that this spectral zeta function has meromorphic extension. To C minus this points n over 2, n over 2 minus 1, n over 2 minus 2, so on. That's one thing. Okay, that's the first thing. Second, SO equal to n over 2 is a pole. Is a pole always, and residue at zeta m s at s equal to n over 2 is given by volume essentially. So thirdly, all other poles. So be very careful. We are not saying that other points are necessarily poles. We are just saying that if there is a pole, it's going to be among these points, but some of them may be missing. Maybe they are not poles. That's quite possible. We'll see examples. All other poles are simple. That's important. There are no second order poles or anything. All poles are simple. And residues, if you compute residues of zeta ms at s equal to these poles, possible poles n over 2 minus k, they are related to heat kernel coefficients, right? Are related. I mean, by this simple formula, are related to because some AKs may be 0. We saw that a lot of them are 0 in case of, for example, flat tori, right? Except the first term, all of them are 0. So they're not going to be poles related to heat kernel coefficients. I mean, basically, the formula that we found is that indeed the residue at this point, so let me write it, at s equal to n over 2 minus k is equal to ak over gamma of n over 2 minus k, or pi to the power n over 2. Right? I mean, residue of this function. There's not going to be contribution from any other points. Okay, so that's what we wanted to do first. I mean, this zeta function, which was completely mysterious, there's no reason to have analytic continuation and all that. There is a meromorphic extension. There is a top pole. And the residues at subleading poles are related to heat kernel coefficients. All of them are related to heat kernel coefficients. So any questions?
I have a question.
Yes.
From the heat kernel, we have this spectral invariance A0, A1, and so on. Now, the partition function and zeta function both seem to be different ways of packaging this invariance up, and so you can extract this invariance by different ways. But I'm wondering what new information we get by considering these different packages.
Yeah, that's a very good question. So we will see soon that some information can be expressed better in terms of zeta function compared to theta functions. I mean, there is simply no other way around it. I mean, we'll see. I mean, I will give you one example soon, so that we just cannot express it in terms of this state of heat kernel. If you just had heat kernel, there would be no way to talk about that invariant.
Oh,
So yeah, so that's quite quite a thing. I mean, zeta function, it's, for example, like, as we'll see, like the classical zeta function, packs information in a way which is kind of superior to everything else in a way. But we have to see this. It's not very straightforward, I know, but that's an excellent question. It looks like mechanically we can go back and forth because you can do Mellin transform backward and get that, but there is more to this story. I'll give you an example of this. That was a very good question. Any other questions or comments?
Is it so maybe I just missed what you said here, but why was the first part, so you broke up this zeta function into the part 1 and part 2, and we showed that the second part was holomorphic.
Yeah.
How did we show that the first part was holomorphic again? I think I missed that.
Well, the first part, we didn't show it is holomorphic. We showed that it's holomorphic away from these points. By doing asymptotic expansion, I mean, just write the definition of asymptotic expansion. It means that, you know, for any, say, k, if you cut the function, say, for any k, after that, I mean, the distance between theta function and the first k terms is going to be of the order of t to the power k plus 1, for example, right?
Okay.
That will show that if you discard terms of power k plus 1 and above, that's not going to disturb. The integrals are going to be convergent and holomorphic. Again, the remainder is going to be holomorphic. So the residues are going. And those first k terms give you an analytic function with those points, residues, I mean, sorry, poles at s equal to n over 2, n over 2 minus 1, up to n over 2 minus k. You see? So yeah, you can then step by step analytically continue up to point s equal to n over 2 minus k. And then as k goes to infinity, you see that your function is actually holomorphic, is meromorphic everywhere. And that's where the poles are. Yeah.
Okay.
So the essence of the argument, though, is this sort of calculations. But to write it in terms of asymptotic expansion and kind of epsilon delta arguments, it's not, you don't see. But no, this was a good question. Yeah. Yeah.
Another question.
Yes.
So in the calculation, there were two terms. There was this Zm of t, and there was -1. And there was one singularity, well, not really one singularity, infinitely many singularities from this second term.
That's what you're doing here?
I mean, there was this 1 over gamma of s plus 1 term, which came from the integral of t to the s dt over t from 0 to 1.
We didn't have s plus 1, though, did we?
Well, it was written on the blackboard like 1 over s times gamma of s.
Oh, that's this part. Minus basically dt over t to the s over t dt. Yeah.
Yeah. So what I'm wondering is that this thing has additional singularities at negative values of negative integers.
No, it doesn't. It's 1 over gamma.
It's a 1 over gamma. Oh, sorry.
Yeah, it's I mean, gamma function, it works like magic. I mean, it's unbelievable we have this. Yeah, it's
Okay.
1 over gamma, so it's all fine except that 1 over s, but that's killed by the 0 of 1 over gamma at s equal to 0. So this function is holomorphic. Yeah. Okay, but now we can say more. Now, this is another beautiful thing about this thing, that we can say more about the structure of poles and things. So let me just tell you what we can say in this case. So moreover, so 1, I start from 1 again. Moreover, this zeta function is always regular at s equal to 0. Zeta and s. Remember, M manifold without boundary is regular at, regular means holomorphic at s equal to 0. You see, that's quite valuable. So you start at this point. This is a pole, certainly. Then come one down. We don't know what it is. Maybe pole, maybe not. But 0 is always regular, no matter what. So this is n over 2 minus 1, n over 2. 1. Of course, if n over 2 minus k, so if dimension of manifold is not divisible by 2, is odd dimensional, this is obvious, right? You're not going to get 0 as dimension of m over 2 minus k, because it's odd dimensional. But you may guess that for even dimensional manifold, maybe there is going to be a singularity at 0, because from 1 to 3 here, it doesn't imply that 0 is not singular. But it's not. And the reason is that, again, we have got this function 1 over gamma s. And 1 over gamma is regular at s equal to 0. So, that's a simple pole, and that kills that possible pole. The reason is that 1 over gamma s, a simple pole. So this is very important. The fact that the zeta function for closed manifolds without boundary is regular at s equal to 0. It's a very important thing to bear in mind. Now, I want to give you as an exercise to also prove, because it's good to think about it. I was going to prove it, but now somehow. So let me just tell you a second. Show that if dimension of M is even, then all poles of spectral zeta function are in this interval 1, 2, up to, are in 1, 2, So in other words, if dimension of your manifold is even, you cannot have infinite number of poles. All poles, this is the top pole and over 2, and then this is regular, and you come one by one down. Well, we are not saying all of them are necessary poles, but if there are poles, they're going to be in this finite list in dimension of m over 2, basically, essentially, and then there are no other. Here it's regular, but if dimension of m is odd, this sort of singularities could emerge at infinite number of points. But if dimension of m odd, possible to have poles at all negative points. So I invite you to think about it. I mean, it's not difficult, but it's a good idea to kind of think about this a little exercise. Okay, so I think it's a good point to stop now, and then when we come back, we shall. Okay, so this whole thing that we did is in Riemann's paper. So let me just. But in his case, he could do more. So, of course, zeta s is equal to sum 1 over n to the s. So to do analytic continuation of this, I mean, okay, so this is first defined for real part of s bigger than 1, right? To do analytic continuation, Riemann gave two proofs of analytic continuation. I mean, meromorphic extension or analytic continuation. So it is in his second proof, is what we just used, the idea. What we used. So if you open Riemann's 1859 paper, as I said in the first 3 pages, 4 pages, he gives 2 proofs. The second proof is an idea. So we used the second proof is what we used today. So what he did, I mean, we just said, okay, this is sum 1 over n to the s, and from 1 to infinity. Exactly, this is equal to 1 over gamma of s, integral from 0 to infinity, sum e to the minus nt, and from 1 to infinity, t to the s over t dt. However, he did something very smart. He didn't approach it like this. He did it like this: sum n squared s over 2, and from 1 to infinity equal to 1 over gamma of s over 2, integral 0 to infinity, exponential of minus n squared t, I mean sigma, and from 1 to infinity, and then t to the power s over 2 over t dt. And you notice here a very well-known function. So that is theta of t over pi minus 1 over 2. So that's where this function is. So you see theta of t is sum, the theta function, exponential of minus pi n squared t, right? N belonging to z. But here he was summing from 1 to infinity, but this function is even in n. So positive, negative, they are the same. At 1, you subtract 1, divide by 2, you get this. Okay? So this is equal to 1 over gamma of s over 2, integral from 0 to infinity. Let's call this function, okay, I don't know, maybe I don't want to give a name to things that are so sacred and, there's like almost like religious, I mean, sacrament about these things. I mean, you should not start changing these terms, or notation. So I don't dare to do that. So this is theta of t over pi minus 1 over 2, t to the s over 2 over t dt. Now, we did exactly the same thing today for general manifolds. And then what we did, we replaced this. Okay, so and then you just write it as sums of two parts. Integral from 0 to 1 plus integral from 1 to infinity. And we used asymptotic expansion near 0 for this part. And this part we argued is analytic. But what he did, he knew more. He knew more about this function, right? He knew that the function that appears here is not just asymptotic. So, the formula that we have is theta t is asymptotically 1 over, root t, right? But he had more information. This is Jacobi inversion, yeah? Theta of t is actually equal to 1 over root t, theta of 1 over t. Right? So you have an exact result about this term rather than asymptotic information, which should be theta t equal to 1 over root t. If we just use this, we'll get what we did today for this special case, no more. But Riemann had this. And then what he did, he could change this integral to this integral by changing t to 1 over t and using this identity. Okay? So at the end of, 2-3 lines, you can just derive the following result of Riemann. That C of S, let me call it maybe Z of S equal to pi to the power minus S over 2, gamma of S over 2, zeta of S. So this function Zs is holomorphic on C minus 0 and 1. This function, we know that is holomorphic because zeta is holomorphic away from 1, and there is this gamma is holomorphic away from 0 and everything else. And so the only singularities of this function are at 0 and 1, and they are in fact simple poles. That's it. So with this, and this pi is this pi, and gamma is over there, and okay, so this is easy transformation, but you have to be careful, and you did all this. So so then we have this theorem, which is both a functional equation and of course analytic continuation at the same time obtained. So the functional equation is that Zs equal to Z1 minus S. So in other words, with respect to reflection, with respect to line S equal to half, this function is symmetric on two sides. Right? Just get symmetric. So this is this famous functional equation. Okay, so the point of this is that if you have more information about heat trace or theta function, in this case like this, then you can do more about your zeta function and you can prove functional equations like this. But for general manifolds, there is no way to get functional equations. This is a kind of higher symmetry here that you have. Another thing is that since this function now, since gamma of S over 2, okay, has poles at s equal to minus 2n, negative even integers. Even integers. Okay. And then this theorem implies that, I mean, the fact that Z of S is holomorphic actually holomorphic on C minus 0, 1, this certainly implies that this zeta function itself, once you analytically continue, has zeros at negative even integers, right? So it implies that, okay, so this function we know is holomorphic everywhere except at 0 and 1, but this function has poles at negative even integers. So we conclude that zeta s at s equal to minus 2n is equal to 0 for n bigger than equal to 1. Okay. And these are called the trivial zeros of zeta, right? So trivial zeros. Zeta. So again, I mean, in this picture that we have here, so let me maybe draw it here. This is 0, this is 1. Now here, below 0, we have minus 2, minus 4, minus 6. These are zeros, right? I mean, in this part, there is no other zeros. And so let me put it like that. And no other zeros on real part of S bigger than 1 or real part of S less than 0. Why? I mean, for example, why zeta function has no zeros here and then no zeros over there. Let's look at the right-hand side. The reason that this function has no zeros, of course, if you are on the real line, it's clear that this function is positive even on the real line. So it doesn't have zeros, but it might have zeros if you go to complex plane. But there aren't. And the reason for that is Euler product formula. So another magical thing about Riemann zeta function that we don't have for spectral zeta functions in general is this Euler product formula. Euler product formula. Which says zeta s. Okay, so zeta s is equal to product of 1 minus 1 over p to the s minus 1 p primes, right? P primes. So this is this. So this is true for real part of s bigger than 1. You can just check this using uniqueness of prime, uniqueness of factorization of integer into primes. You can check that. Okay. So this implies that because this function doesn't have zeros and this is infinite product is convergent, and unless each term is 0, there's no way to be 0. So this implies that no zeros on real part of s bigger than 1. And by this functional equation, except for these trivial zeros, which has to be there, there are no other zeros. So you see, you have to be playing well with this gamma of s over 2. So that's okay. So that's so kind of first step in in Riemann zeta function, of course, the conjecture is that, so beyond these trivial zeros, the only other zeros are going to be on the critical line. Real part of S 1/2. That's the conjecture or hypothesis. Again, we don't have anything like this for spectral zeta functions in general, but you're going to define some analogs of this zeta function for hyperbolic manifolds, manifolds of constant curvature -1, compact hyperbolic manifolds, for example. And we will see that there is, in fact, a Riemann hypothesis for them. That's true. An existence of that Riemann hypothesis, validity of that Riemann hypothesis, I should say, implies some very nice result about the growth of lengths of geodesics on these Riemann surfaces. So it gives lots of information about, so this is called geodesic, prime geodesic theorem for Riemann surfaces. So we will look at that, but this is kind of a blueprint. I mean, so this paper of Riemann, it's unbelievable how many things was able to be achieved in mathematics using just one of the ideas he was introduced. This is the second proof. But then he had other ideas in the paper. The paper is 8 pages. The first 3-4 pages, these 2 proofs, and then we continue. Okay, I wish you one day you will understand all of that paper. So that would be because it would be something really great. So I just stop and then